Okay, I think we will get started. Anyone else joining, they won't miss out on too much. But welcome to today's presentation on pavement drainage, which is an important design consideration for all types of pavements. My name is Gordon Stevens, and I'm the Technical Manager for Geofabrics New Zealand, with over 30 years experience in the design of structures, pavements, and a whole range of different civil engineering applications using geosynthetic materials. We've allowed around 50 minutes for this presentation, and there will be some time afterwards for questions. You can enter your questions in the Q&A session, and I'll have a look at those at the end of this session. The webinar will be recorded and will be made available at a later date. So we'll start this session by looking at the historical significance of drainage, then look at some basic design concepts, followed by a run-through of the design approach presented in Part 10 of Austroads' Guide to Pavement Technology. And then lastly, we'll look at some constructability aspects for pavement drains, and finish off, obviously, with the Q&A session. So moving on to history. So the ancient Romans placed a high importance on managing the movement of water, as highlighted by this Greek historian and teacher during the reign of Emperor Augustus. The efficient use of drainage systems and roads with layers of aggregates is highlighted in that graphic image shown on the right. And a lot of these types of roads can still be found in use today. And here are some examples of other quite old roads with good drainage, and the drainage has ensured longevity of these particular roads. Moving forward in time, we have John McAdam, who emphasized the importance of drainage. This is the document that we can refer to, where he talks about some observations in road construction. Now, clearly, these days we can make roads a lot stronger than back in 1821, but strength alone cannot overcome the problem of drainage. It's an area we still do not put enough emphasis on as much as we should when it comes to design of pavements. Harry Cedergren from the United States is an acclaimed, or was an acclaimed, civil engineer for his work in the area of seepage analysis and drainage design, and published numerous works on the subject. And what we can see are some charts showing the performance of pavements, both poorly or undrained systems and well-drained pavements. And you can see quite a remarkable difference in the working life of the undrained or poorly drained pavement versus the well-drained systems. And clearly this comes at a cost, and that's a sort of indication back through to 1990 of the dollar value in loss due to poor drainage of pavement systems. So why has it been such a struggle to get good drainage designed into roads? It possibly comes down in part because the effects are not immediate. But obviously, all we have to do is wait for some rain, and we start seeing these issues. So why is this drainage an issue for pavement engineers? Intergranular stresses develop in well-drained aggregates, resulting in lateral spread of the wheel loads, as shown in the diagram, which I'll highlight over here. So these intergranular stresses. Under saturated conditions, this load spread is reduced because we lose these intergranular stresses. So the pressure is applied directly down onto the subgrade. Our design theory relies on development of these intergranular stresses. So it is important that we achieve good drainage in our pavements. Here's a demonstration of the influence of water on the performance of base course aggregates using a repeated load triaxial test. So you can see this 40 millimeter down base course material in the dry state, achieving 4.5 million equivalent standard axles to get to a 10 millimeter rut depth. The same sample, when saturated, only gets down to 2,000. So we want to avoid saturation of our aggregate layers for any period of time where the pavement is under traffic loading. So moving on to design concepts. And I suppose the key question is, why do we need to control water in roads? Here we can see water entering the road through cracked surfaces and through edge joints. And this is nothing new. You can drive after rain events in Australia and New Zealand, and you'll see very similar situations. Excess moisture weakens a pavement structure, resulting in block cracking, which ultimately leads to potholes and edge cracking, which is shown over here, some more extreme examples of edge cracking and potholes. Now, where does this water come from? And as you can see in the diagram, it comes from a range of different sources. We're going to be focusing mainly on the water entering in through rainfall events through the pavement surface, but there's also water entering in from the laterally from the edges, and from seeping upwards from groundwater and springs, etc., as well as capillary rise. So the focus in this session is really looking at the water coming through the pavement. And some of you may ask, well, it's a sealed surface. Why would you get water coming through that surface? What we see here is the results of some research carried out in New Zealand, where they looked at a number of sites in the North Island, Wairarapa, Hutt Valley, and Hawke's Bay regions. And they took core samples and carried out permeability testing under varying pressures, 100 kPa to 300 kPa. And as you can see, there's a reasonable amount of water that enters the pavement, bearing in mind that the typical pressure under a wheel is somewhere in the vicinity of 500 to 700 kPa. So we're getting a fair amount of water going through. Some observations from this is site H included a polyester paving fabric, hence the lower flow rate entering into the pavement through the surface. And site E actually had a bitumen-bound base course. But even then, you can still see that there's water entering through into the pavement. So what should our strategy be? Now, clearly, it would be nice if we could prevent any water from entering the pavement. So we should be trying to limit water from entering the pavement from all sources. Ensure there's an adequate pavement crossfall so that any water drains off quickly. The selection of the granulators is important, so any water entering into the granulators should be able to move through those granular layers quickly, and obviously provide surface and subsurface drainage channels to remove that water as quickly as possible out of the pavement. And this is not too dissimilar to what the Romans did many centuries ago when they designed their pavements. So we're not talking about a new strategy. Romans did a good job back then, and we need to learn from history. So what are the challenges? Pavement aggregates present a dichotomy for pavement engineers. And why I say that is that when selecting your aggregates, you want to go for a broad grading with fines to fill the voids, because you want to achieve a high level of stiffness to spread the loads, and good resistance to permanent deformations over a period of time. At the same time, you also would like to achieve an open grading for permeability with low proportion of fines, allowing rainwater to drain through the pavement and preventing development of pore pressures under trafficking that would reduce the strength of the pavement layers. So permeability and strength are not easily achieved together. And when it comes to drainage, efficient drainage is therefore required, as our main design focus is weighed more towards the broader graded aggregates for stiffness in our pavements. The Guide to Pavement Technology, the Austroads Guide to Pavement Technology on Subsurface Drainage, offers a good guidance on this important area of design, and this is what we're going to be focusing on in the coming slides. So let's look at the design steps included in this technology guide for drainage. We start off looking at estimating the inflow entering into the pavement. We then look at the seepage moving through the pavement into the drains. We need to look at the filter permeability and trench requirements to meet the inflow criteria. We also need to check the compatibility of these filter materials with the surrounding soils and the pipe system that we're using. And lastly, we need to select the appropriate pipe size for our drain. Okay, starting at step one, which is the estimating the inflow, we need to determine the infiltration entering into the pavement. So R max is the 1 hour rainfall intensity to determine the volumetric flow in meters a second. The infiltration rate is equal to a 1 hour rainfall inflow multiplied by the infiltration coefficient. So it's difficult to estimate these coefficients, but there is guidance to help us out with that. So this is a table of the infiltration coefficients for different seal types that we use in design. Bearing in mind that when we are considering the infiltration into the pavement, we are looking at both the pavement section and the shoulders. So these will require different infiltration coefficients. So we need to calculate the inflow, and this is taken over the one side of the pavement. So you're looking at your lane, single lane or dual lane, and your shoulder. And you need to calculate the inflow over each of those widths, add them all together and multiply that by the hydraulic gradient. And in this case, hydraulic gradient is 1 for water entering into the pavement. So looking at an example, what we have here is a 3.75 meter lane and a 2.5 meter shoulder. Here's the formula that we use, and we can calculate that for a particular rainfall event, in this case 20 millimeters an hour. So we've got these different surfaces, different rates of inflow, and we calculate that out, and we get 6.94 times 10 to the minus 6 meters cubed a second per meter of carriageway entering into the pavement as our Q value. Step 2 is looking at this water moving through the pavement layers over here. And we need to ensure that that water is allowed to flow through these layers. So we need to consider the permeability of these particular layers. So looking at these layers in a little bit more detail, we need to ensure, first of all, that the permeability of the pavement layers is greater than that of the surfacing, and the same thing is greater than that of the shoulder. We can use Darcy's law and consider laminar flow conditions and apply this formula to calculate what the permeability is going to be. In this case, we're looking at a hydraulic gradient, typically in the order of 3%. It varies, but somewhere around 3% is what is normally considered. So to calculate that permeability, we rearrange the Darcy's law to get that permeability of that subbase layer. And moving back to our example, here we have a hydraulic gradient. We have a layer thickness for that subbase. We've already calculated what the Q is, and from that point we can calculate what the required permeability of that subbase material is in meters a second, which is shown highlighted in yellow. Step 3 is calculating the filter permeability and trench width. So here the permeability of the filter is looking at the total inflow and your width of your trench, which is typically in the order of 0.2 to 0.5 meters in width. So same example and simple calculation here. We've assumed a 0.2 meter width for our trench. We've got our inflow, and we need to have a filter material having a permeability of at least 3.47 times 10 to the minus 5 meters a second. So pretty straightforward. The more difficult bits come with the compatibility of the filters with soils and pipes, and this requires a little bit more in-depth calculations around filter criteria. So what we see here is common subsoil drains, which consist of some form of granular filter, with or without geotextiles, and some form of drainage pipe. So we've got on the left, we have a graded single stage granular filter. The drain in the middle, we've got a two-stage system where we've got a granular first stage filter with a secondary second stage geotextile filter over here. And then this is another example of geotextile first stage with a coarse granular second stage filter. So what we're going to do as part of this exercise is focus on a granular first stage filter with a drainage pipe in the middle. So check for granular first stage filter design, and then we'll move to the second stage filter using a geotextile either in that instance or something like that. So here are the requirements. So it's a bit of a busy slide that requires a bit of explanation. So the first thing that is required is to check the compatibility of the granular filter with the surrounding soil, the soil that comes in contact with the drain. So on either side of that drain. So this requires a particle size distribution curve for both the soil and filter material, so something along the lines shown in that image. From there, you would obtain your coefficient of uniformity, which is your D60 over your D10, and you'll get various particles, D15s and D85s for the different materials. So first calculation is to check for clogging, and the D15 and D85 filter criteria is really the principal filter criteria to ensure stability and any loss of fines in your drain. So these are important filter criteria, and you can see that's the formula for ensuring that the filter doesn't clog over any period of time. The next check is to check for compatibility, and those are the range of formulas based on the coefficient of uniformity of the soil that you're dealing with. The third check is to ensure that the filter material has a permeability that is greater than the soil, which is clearly a very important and obvious criteria. And lastly, you want to check the segregation. So you want to limit any segregation of the filter. Now, it's always quite challenging to prevent segregation of filter during placement. This can be quite a challenge, but this provides a useful guide ensuring that the uniformity for the filter is less than 20, and also keeping the upper bound aggregates to less than 50. Now, if for any instance we fail with any of these filter criteria, then we need to move to a two-stage filter system. So lining that granular filter drain with a geotextile. So here's the example of these single-stage filter criteria. So what we have here is the PSD for a typical soil, sandy silt in this particular instance. And here you can see the various characteristic sizes that we check for and the calculation of the uniformity coefficient. We need to do the same thing for our filter material, which is a sand. So we do that. And then we do our various checks. And what we find is we satisfy all those criteria. So that particular sand filter that has been proposed is suitable for use with that surrounding soil type. Now, if it wasn't suitable, we would then have to move to a two-stage filter. And in this instance, we need to check the compatibility of the geotextile filter with the surrounding soil. So once again, we require a grading curve, PSD, for the soil, the surrounding soil, so something similar to that. We also need to understand what the opening size, the equivalent opening size for the geotextile, and that's normally carried out by a dry sieve shaking test. And then we need to check for various filter criteria, the first being looking at piping. So this is retention to ensure that none of the fines make their way through the geotextile into your drain. For granular soils, you have a certain criteria for the O90 of the geotextile should be less than or equal to the D85 of the soil. And for fine-grained soils, the O90 for the geotextile needs to fit within those sizes shown in that formula. Secondly, we need to ensure that the permeability of the geotextile is greater than that of the surrounding soil using that formula. So it has to be 10 times that of the surrounding soil. Thirdly, we need to look at clogging of the geotextile. Studies by the US Corps of Engineers suggest that clogging normally occurs if the gradient ratio is greater than 3. So the gradient ratio is a measure of head loss at various points through the soil and fabric system. Typically, what you will tend to find in the case of non-woven needle punch geotextiles is that this is only a problem if you start getting silt contents in the surrounding soils greater than 18%. In the absence of any specific permeability testing, this is the formula that is suggested in the guidance. Next check is check for survivability. So we have to ensure that the geotextile remains intact when it's installed and the granular material is placed and compacted on top of that geotextile. And then we also have to look at durability. In the case of geotextiles, durability is not normally an issue. Most soils are pretty benign, and geotextiles are not a nutrient for any biological attack. So looking at our example again, so this is a slightly different example, but just to give you a feel for how we go about doing the check. Here is the grading of the material. So here we've got a sand surrounding the geotextile. And then we're using, in this case, a Bitum A14. It's got a pore size of 110. And we need to go through these various criteria. So it satisfies the piping criteria in this instance. Because we're looking at a granular material. It satisfies the permeability criteria. We then go into the clogging criteria, and we see that in this instance, it doesn't satisfy the clogging criteria, And this would suggest if a geotextile is to be used, there's a need for a gradient ratio test, which is essentially looking at the long-term clogging potential of the geotextile. And then it satisfies the permeability, the survivability criteria and filtration criteria in terms of various highways agency specifications. And then also durability has to be checked. So lastly, we need to move on to the selection of the pipe size. In the case of Megaflo Green, when it comes to use in these highway drains, the minimum size allowable is a height of 300 millimeters. This is a chart showing the gradient on the x-axis and the flow in liters per minute on the y-axis for Megaflo. And we can use this to determine what the outlet spacing is based on the Megaflo flow rate at that particular hydraulic gradient and the inflow per meter. So looking at our example, we've got our inflow per meter. We select an outlet spacing of 100 meters. So we've got an inflow, we've got a gradient of 1 in 100, and we find that Megaflo 300 at that hydraulic gradient achieves a factor of safety of 2.9. So that would be a suitable outlet spacing for Megaflo 300 in this particular application. So moving on to constructability. So within the guidelines, they show a number of different types of pavement drains. So we've got type 1 over here, where you're looking at a granular filter, so a single stage system with a round pipe as your collector. Pavement 2 is a geotextile wrap drain, so that would be a 2-stage filter system. Type 3, we've got a 2-stage filter system with a granular drain and a geotextile wrapped around the pipe. And type 4 is a geocomposite strip or panel drain system with a granular filter. And this is a typical of a Megaflo Green system. And what we're going to do is we're going to look at the comparative installation criteria and performance of 2 of these types of drains. First is looking at the bedding layer. So here we've got your pavement type 2. So we've got a wrap drain with a geotextile wrapping and a slotted pipe in this instance, 300 millimeter wide drain. And if we zoom in on the round pipe, you'll see that we need a bedding layer. And to support that particular drain, and you'll need a fill underneath that. So that dictates that there's a minimum criteria for compaction of that fill to support that round pipe to prevent its collapse. In the case of Megaflo, you can get away with a narrower drain because in the case of Megaflo, the haunches are a lot smaller, typically around 84% smaller. So we don't have the same issue as you would with round pipes. So no need for a sand bedding layer. Next consideration is the geotextile filter. So looking at pavement drain type 3, which has got a filter fabric around the outside, and we'll compare that to drain 4 with the Megaflo. So here, a lot of the round pipes come with a knitted sock. It should be noted that because of the large opening size of the knitted sock, somewhere around 600 microns, there's no real filtration ability. So you really need to use it with a quality drainage filter, essentially a single stage drainage filter for a knitted sock. If you go with a round pipe with a bitumen wrap, then that would be suitable, because that would satisfy the filter criteria. When it comes to Megaflo, that comes with the bitumen already, so there's a lot more flexibility around the type of granular drainage material required for your filter. If we now look at performance, and we'll start off with laboratory performance, and this is a falling head test looking at the discharge of water from 400 millimeters down to 100 millimeters. And what we can see is that a round pipe discharges around about 66 seconds, whereas Megaflo 300 is around 17 seconds. So the Megaflo is able to remove that water out of that pavement or out of the drain a lot quicker. And this will be highlighted later on. And as we've already attested to earlier on, we want to keep that pavement as dry as possible and remove the time or reduce the time for saturation. So why is this the case? And what we need to focus on here is the infiltration area. So we've got a lot larger clear water opening area with the Megaflo drain compared to round pipe. So we can remove water a lot quicker with Megaflo. So let's move into the field, and this is a relatively old test, but quite relevant, and this was carried out by the Illinois Department of Transport. And what we're looking at here is the same stretch of road during the same storm event, and this road is all at the same gradient. And here are the results after 2 hours and after 4 hours, showing the amount of water being removed out of the pavement. The section with Megaflo 300 as the drainage, and the other one with 100 millimeter corrugated polyethylene pipe. And in summary, what we're seeing is that Megaflo is removing 36% more water in only 56% of the time. So what I'm going to look at now is a bit of a graphical representation of that particular chart, looking at different stages in hours for this drainage. So starting off at T1, so after 1 hour of this rainfall event. And as you can see, in the case of the round pipe, the base course is fully saturated. Now, just remember back to that repeated load triaxial testing, the reduction in performance due to saturation was quite dramatic. So keep having a saturated base course layer for any period of time will cause deterioration of that particular pavement. In the case of Megaflo, the Megaflo is starting to drain already, and you can see over here, this is the Megaflo line versus the round pipe, and you can see that we've got a higher level of efficiency already at T1. At T2, 2 hours, we can see that level of saturation is extended down through the pavement layers and even getting down to the subgrade, which is a serious concern when your subgrade starts getting saturated, and most of you as pavement engineers would understand soaked CBR is quite different to a dry CBR for a pavement, and that has quite an influence in the overall performance of your pavement. In the case of Megaflo, you can see that the drain is working efficiently with only a small proportion of the pavement at a saturated state. Higher up in the pavement, the subgrade and subbase is essentially remaining in a dry state. At time 3 hours, you can see that the subbase and the subgrade is still remaining quite saturated, which is a concern for this round pipe situation. Certainly the base course is starting to drain. Whereas if we look at the Megaflo, we can see that the pavement is essentially back to near normality, just a slight excess moisture in that base course, draining out of that base course layer. So to put this research into context, we can see some work carried out in South Africa on the effect of excess moisture on the carrying capacity of a pavement. And the curve through the subgrade soils shows the impact on the modulus with increasing moisture above optimum. And that impact on the modulus is quite dramatic, and anyone who's designed pavements would appreciate what that effect will have in reducing increasing the damage to the pavement and increasing your deformations or vertical strains on your subgrade. Right, coming to the end of the session. And just to summarize what we've covered today. Excess moisture in pavements should be avoided where possible. A sealed surface does not prevent water from entering the pavement. Everyone talks about seals, waterproofing seals, but as what's been shown, water can still enter those sealed surfaces, and those sealed surfaces don't always stay sealed. Cracks do occur in pavements, especially when you start using cement-treated pavements. That's the main cause of crack surfacing. When it comes to design of flexible pavements, we consider the materials to be at their most favorable state. Hence, we need good, efficient drainage to support our pavement designs. Obviously, care must be taken when selecting pavement and materials to ensure excess moisture can actually drain out the pavement and you don't end up with a perched water table within your pavement layers. Discharge capacity when selecting your pipes is not the only measure. The speed of water removal is arguably more important when selecting your drainage pipes. And lastly, when it comes to the costs, and something that engineers will always ask, when you look at these Megaflo panel drain systems, typically because it's a less excavation and less drainage fill material, the system comes in somewhere in the order of 15 to 20% cheaper than that of a round pipe system. So that's the end of the presentation, and we're pretty close to our 50-minute mark, and we'll now move into Q&A session, and I'll see that we've got a number of questions that have been raised, so we'll get into those particular questions. The first question, actually, I'll just move this so I'm not looking up at my other screen. I'll just keep it on the main screen. The first question, is there design software used for drainage design using Megaflo? The question is quite relevant. If we go back a number of years, Geofabrics did develop a design software for designing pavements to Austroads. This software has subsequently sort of declined with changes to Windows systems and is no longer operable. However, developing a spreadsheet to follow the guidelines in the guide, the Pavement Technology Guide 10 is pretty straightforward. I've developed a spreadsheet as highlighted in the presentation, and I'm happy to share the spreadsheet. It's nothing too special. So if anyone wants that, they can certainly contact me. I don't have my email address here, but it's simply g.stevens@geofabrics.co.nz. Next question is permeability of CTB, implications of variability on subgrade PSD and geotechnical characteristics, and whether GA makes these design templates available for engineers. Okay, so permeability of some CTB would be cement treated base courses. Good question. Anyone driving along pavements, every day I drive along a road that has a cement treated base course. So it's a common treatment. If your pavement is not working too well, you go and retrofit by treating the base course to improve the performance of your pavement, and that's really great until a few months later cracks occur in the pavement, and you get all this sort of white deposits left on the surface. Certainly, adding cement into your pavement is going to have a big implication on the permeability, and it's going to reduce the flow of water through your pavement, and there's a chance that you would likely fail the criteria provided in the guidelines. Implications of the variability of subgrade PSD. Subgrade PSD we're not too concerned about in this guide, in this drainage method, because we're not looking at water going from the subgrade into your drain. And I've already asked the question about design templates available to engineers. Yes, I'm happy to make the one I've developed available to anyone who wishes to use it, or take it and modify it to their own requirements. The last question is, can Megaflo be used in airport pavements? We're certainly using it in airports. In terms of airport pavements, Megaflo's got a very high crush strength, So it can be used in high-loaded applications. We've certainly used it under rail tracks where you've got high dynamic loading, and it's been tested. We've got a research facility that's the grid that's carried out testing of Megaflo, in this case laid horizontally under rail track to ensure that the Megaflo can survive the dynamic loading from rail. So in terms of airport pavements, there shouldn't be any reason that I cannot see that why it cannot be used in these airport pavements, because it can take quite high loading. We don't have the same level of dynamic loading that you get in rail, but certainly the wheel loads in airports are quite high, so there shouldn't be too much difficulty. But certainly Geofabrics is able to run some tests at the grid, the research facility on the Gold Coast, to confirm the suitability of Megaflo for that airport application. So that's all. Oh, we've got some more questions that have come in. Carry on. Is the granular filter required for all roads in all weather conditions? So the granular filter, there's different forms of granular filter. A single stage granular filter is essentially ensuring that you get no fines coming through. So it's a well-graded granular filter, and will ensure, it will filter out any fines from the surrounding soil. You can also get a more sort of open graded granular filter, which requires the use of a geotextile to wrap that granular filter. So we would certainly, drainage is critical, and it's certainly, you say all weather conditions, you can go from the center of Australia to down south in New Zealand, where you get 4.5 meters of rainfall per annum, and I would say that you would need granular filters in most of these instances, because where you get rain, unless you can be very assured that rain is not going to penetrate into your pavement, then you will need some form of drainage to remove that material, that water out of the pavement. If the pavement is capable of draining that water out without any additional pavement drains, then that would be fine. But obviously you need to match the filtration criteria or the drainage criteria with the load capacity criteria of your pavement layers. Interesting question over here. What is the uptake of Megaflo in Australia and New Zealand? I'm based in New Zealand, so I can't speak too much about the uptake in Australia, but I know in New Zealand we see it widely used in numerous applications. Because it's a pipe itself, it's a flat pipe, but it's a completely enclosed pipe with a high flow rate. It gets used in shotcrete walls. It gets used in rail, as previously mentioned. It gets used a lot in field drainage and in pavement drains as well. Now, I suppose when it comes to pavement drains, round pipe tends to still be used a lot more, but that's only because of historical use and because it's a recipe design without much design input. Essentially, it's more more cut and paste when it comes to the use of round pipe. There are a number of fish hooks when using round pipes, especially with filter socks around them. Round pipe does have an invert, so it does need to be laid correctly, which doesn't always get laid correctly. It's more subject to damage compared to Megaflo. So we see that there is an increasing use of Megaflo in pavement drains, and it's likely to increase. But convenience dictates that a lot of contractors will just tend to historically use round pipe, but that is changing. How do you decide to lay, this is probably, we've got two more questions, so I'll try and get through both of them before the time's up. How do you decide to lay Megaflo, vertically or horizontally? You have 170 millimeters one face, and the width is actually 40 millimeters. So do you generally keep 170 in the vertical direction, but in golf field design, I've seen 170 kept flat on the surface. So it very much depends on the application. Now, in pavement drains, you generally lay the Megaflo vertically, because what you want to do is you want to keep your drainage as high up in the pavement as possible, to be able to start draining the pavement as quickly as possible to remove that water. So in pavement drains, you would certainly lay it vertically. The exception would be if you've got a perch water table, for instance, and you want to sort of lay the drains across the pavement. You could lay it horizontally to minimize the amount of excavation down into the pavement. So that could be used, and the beauty with Megaflo is that it's got the crush resistance to be able to take vehicle loads when laid horizontally high up in the pavement. But generally, we see Megaflo used more in sports fields, in golf courses, and in artificial turf applications where it's laid horizontally. And we have flow rates for both vertical and horizontal applications. So it comes back down to what is the design criteria, what are you designing for in terms of how you lay it. And it's great that the engineer is thinking about the poor contractor having to install it, making sure that it's most cost effective from an installation criteria. Also, this is the last question. If you were designing subsoil drainage to help drain a boggy garden, would F2 sand be your go-to, or would you settle for some P metal? With P metal, you have to wrap the drain with a geotextile because it's quite open, and it would allow fines from the surrounding soil to enter, so you would still need to wrap your drain. With F2, you won't need to, but clearly the F2 graded sand filter is a lot more expensive than P metal. So once again, it's balancing up the cost of the materials and your various design criteria. So time is up. Once again, on behalf of Geofabrics, we'd like to thank you all for attending this webinar, and as I mentioned, the recording for this webinar will be made available at a later date. And thank you all very much for your time, and we'll end that now.